here. All right, yes, can you hear me? Okay, because there's going to be talking today. All right, so we are starting our new unit today. We are starting forces, okay, which you read about for last week, and I apologize if you had to do all that extra reading and then we didn't start last week. So we've talked about acceleration and how acceleration causes objects to move and change direction, change speed, but we haven't really talked about what causes acceleration in the first place. So what causes an acceleration? Dagny. No, a change in velocity is a result of an acceleration. But what is causing that change? Sophie. An external force, okay? So a force is really any interaction that causes an acceleration or that can cause an acceleration. Okay. So usually we think about forces as pushes and pulls, but remember that that's not all there is to it, okay? Gravity might be pushing or pulling, but it's not like there's a string between my eraser and the earth that's pulling it down, okay? Keep that there in case I throw it again. The planets, which is how Isaac Newton kind of figured all this out, are orbiting around the sun. There's no string that connects the earth to the sun and makes it go around in that circle. Again, it's that gravitational force, but it's an interaction and it is a force, but there's not necessarily a contact, okay? Another example is you are sliding across the floor in your stocking feet, okay? And what happens to you if you don't hit something? Lauren? Eventually you slow down, okay? Why are you slowing down? Yeah, there's a friction force between you and the floor, okay? And eventually what direction must that friction force be acting? Opposite to your motion, okay? Because it's decreasing your velocity until you come to a stop. Okay? So Isaac Newton, late 17th century, early 18th century, studied all kinds of motions, and he actually was able to formulate them into 3 laws, which is what we're going to talk about in this chapter. So for most cases involving everyday life, dropping erasers, planets moving around the sun or other stars, Newton's laws describe what we see. But for things that are moving really, really fast, like fractions of the speed of light, or things that are really, really small, like atoms, we need to invoke 20th century physics and use Einstein's relativity ideas for really fast things or quantum mechanics for really small things. So both of those ideas, relativity and quantum mechanics, are beyond what we're going to do here, but it's important that you understand that there are limits to what we can do with Newtonian mechanics. Okay. So let's start with Newton's first law. Which is sometimes called the law of inertia. Okay. So to do this, and to think about Newton's first law of inertia, we're going to do something called a Gedanken experiment. Anybody speak German? Do you ever come across that word? Dalvin Hahn is the only student I've ever had who could actually tell me what that was, and that was because her dad did a sabbatical in Germany and she was able to figure it out. Gedanken means thought. So we're going to do thought experiments. And there are some very famous physicists, including Richard Feynman, who was not a really nice person, but a brilliant man, as often happens. Einstein was pretty much a jerk too. But what they would do is they would think about things and they would make a model in their head. And then they would keep adding aspects, adding ideas, adding conditions, and then the model would break. And Richard Feynman was famous for sitting in the back of a lecture. He was at Cornell for a while. I think he was at Harvard for a while. He was part of the Manhattan Project. But he would sit in the back of the lecture that you were giving on your research, say, and he would build this model in his head. And then all of a sudden, something that you would say would make the model break. And his hand would come up. And it was the dread of every graduate student that he ever encountered that when Dr. Feynman's hand came up, it was all over and you were sunk, because he was going to ask you a question that you could not answer and he was going to point out exactly what was wrong with your research. But ours are not going to be that complicated. Okay, so my first Gedanken experiment is I'm going to take this pen and put it right here. What's going to happen to that pen? What's going to happen, Fiona? Just going to stand there. Okay. I don't know if you can guess. I don't know if you can see. Okay, see, I just have a red marker in there. Okay. So how long is that pen going to sit there? As long as I want it to sit there? Okay, so as long as there's no external force. So pretty much it's going to sit there forever unless I, as an external force, pick it up, or unless there is the vibration of an earthquake, which we get here sometimes, and that vibration might be enough to knock that over. Eventually, the forces in the atoms that are holding the desk together will break, and then gravity will overcome and the pen will go down. So our second Gedanken experiment is about the horizontal component of projectile motion. Okay, so if I took my same pen and I threw it, okay, what's going to happen to that horizontal component? That horizontal velocity that I give it, what happens to it? It stays the same, right? Not the vertical component, the horizontal component. Is there acceleration in the horizontal component? No, and that's why it just keeps going. So why does it like drop? Why does it fall? Because there's a gravitational pull from a really big, massive object, in this case, the Earth. So if I took my pen, say, really far out into space, and again, I threw it, what would happen to it? What, Dagny? It's just going to keep going. It's just going to keep doing whatever it is that it's doing, because there's no gravitational force to pull it to change its direction. Okay? So in these two situations, there's no acceleration. The motion doesn't change. The object just keeps doing what it's doing. And the reason that there's no acceleration is because there are no external forces. So Newton's first law tells us, and you should have it written down already, but I'm going to type it out anyway, just so that we all agree on what it is. That if no net external force acts on a body, then the body's velocity cannot change. That is, the body cannot accelerate. Okay. And when we talk about a net external force, we're saying that F net is equal to 0 in this situation. So sometimes we say this in a little more familiar language, and we might say that bodies in motion tend to stay in motion, and bodies at rest tend to stay at rest, unless acted upon by a net external force. So that's a little more descriptive, but I think sometimes it helps you remember more what it is. And we could even write that down. Bodies at rest, stay at rest. Bodies in motion, stay in motion, unless acted upon by a net. I cannot type when people are looking at me. Okay. Steady.
So when you say body, does that mean that everything, like the body contains like a car, contains more than one object? Does that mean that every single object needs to be, in order for it to be like, in order for there to be a change in the velocity, does that mean every single thing needs to be affected?
We're not going to get that complicated. Our objects are going to be like this. They're not moving.
I was thinking like a car crash, like the person will keep moving.
Right, exactly, they will. Because, so let's talk about a car crash for a minute, which is a good example of inertia. Everything in the car is moving at the same velocity. So let's assume that you're not like rocking back and forth or whatever. So everything in the car is moving with the same velocity, okay? When that car crashes into, say, a tree, the front of the car is stopped. But just because everything in the car has the same velocity and they seem to be touching each other doesn't mean they're attached like a single unit. So the front of the car stops, which stops the car proper. But you, or let's start easier. Let's take the coffee cup that you've got or the bowling ball you have on the front seat next to you. That bowling ball is not attached to anything. It's moving along with the car because we're all moving at the same velocity, but there's no force on the bowling ball to stop it, so it's just going to keep going until it hits your dashboard. Okay. You, who I pray to God are wearing your seatbelts, okay, you keep going too because you're not attached to the car proper. Your seatbelt kicks in, right? Because your seatbelt doesn't restrain you all the time. Your seat, have you ever done that where the car's accelerating and you try to move and you can't? That's because the mechanism in the seatbelt detects acceleration. It's that jerk thing that we talked about in calc the other day. Okay, it checks how the acceleration is changing. So if your car is accelerating, even not dangerously, but if it's changing its velocity quickly enough, it kicks into the seatbelts, and the seatbelt won't let you stretch because it thinks you're in an accident. Better safe than sorry. So the seatbelt will kick in when you start to pull against it because you're still accelerating, and then it'll hold you back. But if you didn't have the seatbelt, you would just keep going, and that's why people go through windshields. Okay. And airbags are different. The purpose of the airbag is to slow you more slowly, to take that force, to take the change in momentum, which you might remember from freshman year and which we'll talk about in several chapters, but to take that change in momentum and spread it out over a longer time, which means the force is less, and force always equals pain. So you want a smaller force so there's less pain. Okay? Pain doesn't have to be bad, but an elephant standing on your foot versus my 19-pound puppy standing on your foot, there's going to be a very different pain threshold there. Okay? All right, we good? Okay, so let's talk about force a little more. I don't have my favorite. Okay, I'll even line up. Yeah, call Gus and have so she can see. Okay, FaceTime Gus or whatever you need to do on your iPad, so that she can see what we're going to do. Because obviously this is just the beginning of. Is she there now? Okay. Because obviously this is just the beginning of what we're going to learn with forces. Okay. So if I push, okay, I'm pushing as a force. If I push the recycling bin that way, which way does it go? The direction I pushed it. If I push the recycling bin this way, which way does it go? The direction I pushed it. So the direction of my force makes a difference, right? And what do we call quantities when it matters what the direction is? Vectors, okay? So force is going to be a vector. And as we've already said, kind of the symbol that we use is capital F. And then we put the little arrow over it. So then, what are the units of force? And that's the symbol I use when I'm figuring out the units. What's the unit of force? Newton. Okay. Which we will abbreviate capital N. You may come across a few things somewhere, a few questions here and there where their N is a small n, but I don't think that's a good idea. And the College Board doesn't do it that way, and your book doesn't do it that way. Because the little n sometimes means nano, and it's not a good. Okay. So again, you probably have this from your notes, but we're going to write it down anyway. 1 Newton is defined as the force necessary to move a 1 kilogram object with an acceleration of 1 meter per second squared. Okay. And then as we'll talk about, this is the first unit that we've encountered, label that we've encountered, that isn't in terms of kilogram, meters, and seconds, which you read about as being the base units. Every unit that we encounter from now on, we can express in terms of those base units. And sometimes you need to do that. So a Newton is a kilogram meter per second squared. And we'll kind of see where that comes from later. Okay. So if force is a vector, that means that I must be able to have multiple forces acting on an object. And then I must be able to add them up, right? Because that's the whole point of vectors, is it's a way for me to take multiple influences and add them together. So let's say again, actually, I'm not going to do that. I'm going to make it blue. Let's say I have my recycling bin and I'm exerting a force on it this way that we'll call force 1. At the same time, somebody else, a straight line, is exerting a force F2. But where's the recycling bin actually going to move? That way? Even though I'm pushing it this way and you're pushing it this way? It's F2. No, it's not. I'm sorry. Excellent question. Let me make that F2 look a little bit better. No, this is an overhead view. Yeah, okay, so I'm going to take my vectors. I'm going to add them tip to tail. So I can take this vector and put it over here. I can take this part of it and write it in here. Okay, so I've got my vectors tip to tail. And then I'm going to have a resultant vector by connecting the leftover tail to the leftover tip. So this might be, in this situation, we could call it F net, because F net just means that I'm adding all of my forces together. Okay, so we could write that down too. That F net is equal to the sum of all external forces acting on an object. Okay. Okay, so we good? All right. So one of the great things about the laws of physics is that we consider them to be universal, which is really important because it means that when we look out into space and we see planets orbiting another star, we assume that we can understand that motion because it's going to work just like that motion does here. Okay, and we can do it with all kinds of things. We can do it with electromagnetic forces that hold atoms together, that atoms are not held together any different on Alpha Centauri just because it's 4 light years away. Okay, but we still have to be careful. Newton's first law only holds for inertial reference frames, which we have read about before. An easy and simplified way to think about inertial reference frames is one where the ground isn't moving with respect to the body. So basically, everything that we do where we attach our coordinate system to Earth is going to be fine. Okay, and Earth's surface works for short trips. Okay, I think we talked about this a couple weeks ago, where the summer I spent calculating missile trajectories. Okay, then the Earth wasn't an inertial reference frame. Okay, but for kicking our soccer balls, even for when we're shooting rifles or cannons, we can assume that the Earth is an inertial reference frame. So it's not really going to affect what we do in here, but there are things that, as a physics teacher, I am honor bound to point out so that you don't go away to college and make a fool of yourself. Okay, or at least you don't do it in physics class on my account. All right, you will make a fool of yourself in college because that's what happened. Okay. All right, we good? All right, so next thing I want to talk about is mass versus weight. Okay, so we have been throwing around the term mass. Okay, we talk about the mass of an object, we talk about a mass that's moving around. It comes up when we're doing our labs. But this is one of those situations where mass has a very specific meaning in the physics classroom, as does weight. Those do not line up with the meanings that we have in everyday life. And I really, I don't know if you read the part where your book talks about this, but I really don't like the way they explain it, okay? Because it's pretty simple. Mass is an intrinsic property of an object. What does that mean? Somebody. No. It means it can't change, okay? That no matter where I take it, no matter what I do, that property is going to stay the same. Okay. So whether I have that mass on the surface of the Earth, on the surface of the moon, on, I don't know where else, I can't think of anything really big that actually has a surface. If I put it out in the middle of space, it has the same mass, which is essentially a count or the number of atoms in that object, okay? So basically mass counts up the number of atoms, the number of molecules, whatever those fundamental little units are. And each of those has a mass, right? When you did mass in chemistry, right? What unit did you use? Moles are different because a mole of carbon could be have a very different mass than a mole of helium. A mole of uranium, a mole of lead, and a mole of helium have a very different mass. But what units do you use for mass in chemistry? You use grams, okay? Because you're talking about things that are so small that using kilograms would be silly. Okay, you're not going to put kilograms of baking soda into vinegar, okay? I mean, we could, it'd be fun, but it's a little out of control, okay? So we use grams and kilograms. Weight, on the other hand, is not an intrinsic property. What's weight? It doesn't change the mass, but it is a measure of the force due to another large body, okay? It's effectively the gravitational force. Okay. So on Earth, weight is how much the Earth is pulling on that object. And the amount of that pull, as we'll learn, is a function of the mass of the Earth, the radius of the Earth, and something called the universal gravitational constant that doesn't change. Okay. But if I took that same mass to the moon, now the moon is the largest body with mass near it. The moon has a different mass. It has a different radius than the Earth. So the gravitational force is going to be different. It ends up being about a sixth, I think, of what it is on Earth. So your weight is something that changes depending on where you are. If you are out in the middle of nowhere in space and there's nothing around you, you are truly weightless, not like the astronauts. The astronauts are not weightless. Okay, they're in free fall along with everything around them. But if I was out, if my spacecraft had gone somewhere and I was out doing an EVA, I would be weightless because I'm not near a large body that's going to be pulling on me. Okay. All right, so we understand that difference. Please do not use them interchangeably because they really aren't. Sophie. No, in theory, you have a gravitational force. The reason that Fiona isn't orbiting around you, or more likely that you're orbiting around each other, is because that gravitational force is so small. And the gravitational field of the Earth overpowers that. A field in my I don't know, the way I explain a field is it's a set of instructions that exists, whether or not you're interacting with that body or not. So I could get ready. So if I put my eraser here, when I let it go, the field of the Earth tells that eraser that what you need to do is move down at a certain acceleration. Okay. So that gravitational force is what we call an inverse square law. So the gravitational, and we'll get to this formally later, much later, okay? But it's a good question. So the M1 and the M2 here would be Sophie and Fiona's mass, okay? Probably something on the order of 50, 60, 65 kilograms, okay? So let's just say that we'll let M1 be 60 kilograms and M2 be 65 kilograms. Okay. R is the distance between them, which we all hope is 2 meters. Not quite sure today, but all right. And the stickler here is this capital G, which is the universal gravitational constant, which means we believe it is the same everywhere, which is what allows us to say, okay, those planets orbiting that other star, we can use them to figure out what the mass of the star is, which is something else we'll talk about. So this is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. For that, no, I wouldn't now. This is not this chapter. This is just a Sophie asked an interesting question, so let's go with it. Okay. So if we substitute all those things in, what do we get? Make sure you put parentheses around this when you substitute. What do you get? What'd you get, Fiona? That was your look of shock. That's enough digits times 10 to the. Is that what other people got? Ish. Yes, it does. What'd you get?
I got 6.50 times 10 to the negative 8.
So what is it? 6 point.
6.50.
No. It's in the numerator of the fraction, or it's next to the fraction. It doesn't matter. But no, it is in no way, shape, or form in the denominator. Okay. So that's the force between Fiona and Sophie. Okay. If we again let M1 be 60 kilograms, if we let M2 be the mass of the Earth, which is 6.998 times 10 to the 24. I think that's right. 5.998 times 10 to the 24. Mostly because, like, I don't understand why we can't just call it 6. That's why I wanted it to be 6. Okay. the radius of the Earth, which is effectively what little r is, because it doesn't really matter that you're 20 meters off the surface. That's times 10 to the 6th meters, but I don't know what it is. Fiona's going to look it up. It's an R. It's really hard for me to write at the bottom of the screen. Radius, yeah.
I believe in 6. I got 6.27 million.
So million is 10 to the 6th. I knew it was 10 to the 6th. And G is still the same. So if you put all that in, what's the gravitational pull on one of them? In the Earth. What'd you get?
6.411 times 10 to the negative 1.
No. No. It should be something like 60. 600, excuse me. It should be 600.
3.76 times 10 to the.
No. That sounds right. 60 what? So 603.
So the gravitational force of M2 is the same, just R is changed.
No, M2 has changed because now M2 is the mass of the Earth. Okay. So the Earth is pulling on Fiona with a force of 603 newtons. Sophie is pulling on Fiona with a force of 6.5 times 10 to the negative 8 newtons. Fiona feels the force of the Earth. She's not going to feel the force of Sophie. Dagny. Well, think about how many orders of magnitude that would have to be. There are experiments where, yes, you walking into the room would change that experiment. But it would have to, we're talking like atomic things or smaller. Okay. Sophie.
And I got my hand like ridiculously close to the table. And so this happened to be on the table. It was gravitational.
But the thing is that, see, and actually I'm going to change my, the thing is that no matter how small that particle is, the pull of gravity of the Earth is going to be bigger. It's a combination of, if you look at the formula, okay, it's a combination, of the distance and the mass. So maybe you could make, if you're talking about it being the same, if you're talking about keeping like, no, it's still, the gravitational force of the Earth is still going to win. Okay. And in your situation with COVID, there's a whole bunch of other stuff going on. Okay. The reason probably that the COVID or the germs or whatever are sitting on the are stuck on the desk is probably electrostatic, which means there's some static electricity involved. And there are some other kinds of molecular bonds that are involved. So it's not just that gravitational pull, there's all these other things that you have to deal with. Okay. So this was a pretty complicated way to figure out basically what Fiona's weight is, right? Okay. So I'm just going to write this formula again. I'm going to call that M Earth and M person, and I'm going to divide that by R Earth squared. Okay. Just as a little preview for what comes next. Okay. Because this is a pain in the butt. Okay. But if we assume that everything that's sitting on the surface of the Earth is at about the radius of the Earth, and there's some things wrong with that, okay, that we'll talk about later, like Earth is not a sphere, it's a smushed basketball. So things at the equator are farther away from the center of the Earth than things at the poles. It spins, which screws everything up, but we are so far away from ever dealing with the spin part. Okay. And the mass of the Earth is going to be the same. It turns out it's not uniform, which is going to be a problem again that we'll talk about later. There's a weird thing that happens over the Indian Ocean that messes up satellites and stuff. And G is the same because it's the universal gravitational constant. It needs to be the same everywhere. So basically, these things are going to be the same for everything on the surface of the Earth, or at least close enough for Newtonian mechanics. So what we're going to find many, many months from now, and what you'll read about when you read about the different kinds of forces, is that this is actually going to be equal to the acceleration due to gravity. So that when you want to find the gravitational force or the weight, and I will not use those symbols. I will not use W for weight, okay, because there's too many other things that we need W for. That's just going to be your mass times the acceleration due to gravity. Okay. And that's part of yeah. So I don't know what it says, but your assignment for tomorrow should be to read 5.6 common forces. Is there any assignment on the portal? Because we're behind. So you were supposed to read 5.6 for today and you did? Okay, good. Then there's no homework for tomorrow. Okay, because we'll talk about the common forces tomorrow. And then I want you to do an exploration before you read about Newton's second law. Okay, so I will update the portal at some point, but don't read any farther. I don't want to spoil you. I want you to do the exploration with an open mind. Okay, so then this equation should not be a shock to you because you should have read about those forces for today. Okay. All right, are we good? Okay. So when we solve problems, we are going to use the same principles that we've been using all along. Okay. We are going to start by doing what? Drawing a picture. But the thing is that when we do force problems, we need to draw two pictures. You need to draw kind of the picture that we've always drawn, which describes the situation, which shows you all the pieces and how they interact and where the ropes are pulling from, and it has a positive X and Y direction. But then you need to draw something else, which is what? A free body diagram, okay? Which helps us organize our thoughts about forces and helps us organize our forces. And when you have multiple objects, it helps you figure out which forces go with which objects, okay? So there are some rules for drawing free body diagrams that you were supposed to have watched videos about. Okay. But basically, you start by drawing the object. You can make it be a dot, because at this point, we assume that all the forces are kind of acting on the center. I would not get crazy about trying to draw armadillos, so I would go with a box or a dot. Okay. And then you draw the forces. Okay, so if I have force A acting this way and force B acting this way, the lengths of my arrows indicate the relative magnitudes of my forces. You do not need to get out a ruler and set a scale and do all that, but it should be true that the magnitude of FB is greater than the magnitude of FA, because I drew my FA arrow longer. And then, of course, don't forget to draw your axes. Okay. So I want to end by doing an example problem that you should have in your notes. Okay. So I could actually find that example problem. This is the wrong class because I was obsessed with the fact that I did not have the right notes for this for the other class. Yes.
When we draw our axes next to our forgotten line diagram, should we put positive or negative symbols next to the F naught?
Yeah. If there's no positive sign, it is assumed that it is the positive direction. Okay. All right. So there are three forces acting on a particle that moves with unchanging velocity. If there's no velocity, what does that mean? No acceleration, right? Okay. Two of the forces are, and I'll write these again just because the symbols didn't really come out, are F1 is equal to 2 newtons I plus 3 newtons J plus negative 2 newtons K. And the other one is that F2 is equal to negative 5 newtons I plus 8 newtons J plus negative 2 newtons K. Okay, you don't have to write those down again, you have them. What is the third force? Okay. So if the velocity isn't changing, and that means there's no acceleration, what else does that mean? Dagny? F net is equal to 0. Okay. So what we need to remember is that F net being equal to 0 is really 3 equations. Okay, because just as with everything else that we've done, what happens in my y direction and my x direction and my z direction are all separate, and they do not impact each other. They don't change each other. They don't affect each other. So this is really the same thing as saying that F net in my x direction is going to be equal to 0. And I'm putting a vector symbol over that because I want to remember that they can be plus or minus. Okay. F net y is going to be equal to 0. And F net z is going to be equal to 0. Okay. Okay. Now, if I only had forces in 2 directions, if I only had them in x and y or I and j, I'd probably put all my forces on the same diagram, okay? And that's what we'll do because I don't know if we'll ever again have forces in 3 dimensions. But because it's really hard to draw in 3 dimensions, I'm going to draw a free body diagram separately for each direction. And I can do that. There's nothing wrong with that, okay? So let's draw our free body diagrams, okay? And let's start with X. So I'm going to draw my box. And then I have a force from F1 and a force from F2. So I'm going to let this be positive X and this be negative X. Okay. And then what is my force in the X direction from F1? What is it, Annabelle? Positive 2 newtons, okay? So I'm going to have F1X, and that's going to be 2 newtons. Okay. Fiona. Doesn't matter. At this point where those forces act, does not matter. Okay. I try to make it start at the center. It's just sometimes hard with the pen. Okay. So how about my F2X? What's that equal to? -5. So that needs to be longer. So this is my F2X, and that's -5 newtons. -5 newtons. Okay. And then I can draw a similar diagram for Y. I'm going to let plus Y be this way and minus Y be that way. And what's F1Y? +3. And what's F2Y? So I have to have something that's a lot longer. And then again, I can do the same thing for my Z direction. -Z, +Z. What's my F1Z? Okay. So F1Z is -2 newtons. And what's F2Z? Okay, so those should be identical arrows. Okay. Now remember, I have some mysterious third force. Okay, so I'm just going to write down here that I've got F3, and it's going to be F3X times I plus F3Y times J plus F3Z times K. Okay. I don't really know what F3X, F3Y, or F3Z are, so I'm not going to put them in my picture, but they need to be there, okay, in your head. Because the whole thing is that F net X, that's a little comma there, is equal to 0. And remember that we said at the very beginning that F net means I add up, that's a sum symbol, I add up all of my X components. So that means I'm going to take F1X plus F2X plus F3X, and they all have to add up to 0. So F1X is 2 newtons, F2X is minus 5 newtons. I don't know what F3X is yet, but I know that when I add those all up, they have to be equal to 0. So what's F3X going to be equal to? 3. Okay. I can do a similar thing for the y direction. F naught y is equal to 0. And again, that means that I've got F1y plus F2y plus F3y, and those are all going to be equal to 0. So I can substitute in. I've got 3 newtons plus 8 newtons plus F3y is 0. And so what's F3y equal to? Negative 11. And finally, I can do the same thing for the z direction. F1z plus F2z plus F3z is equal to 0. And again, I sub in, so I have negative 2 newtons minus 2 newtons plus F3z is equal to 0. Or F3z is equal to, not negative 4, 4 newtons. Okay. So my answer here is that F3 is equal to 3 newtons I plus negative 11 newtons J plus 4 newtons K. Okay. Right, and we will do more with free body diagrams. This was what I had planned to do last Thursday, but things happen. So we will talk about what I call hidden forces on tomorrow, and those are the common forces. But what that means is they're forces that they don't always explicitly tell you about, but you need to know that if the pen's sitting on the table, there's a gravitational force pointing down and a normal force pointing up. We'll go over that real quick. I found an interactive where you can draw free body diagrams and they will check them for you. So we will do that tomorrow too. And then we'll start the PhET exploration and hopefully we'll get to Newton's second law. Okay. All right. So if there are no questions, pack your stuff up. Guess you okay? All right. See you tomorrow then.